In science, we're always trying to put our ideas to the test. We look for evidence, experiments, and confirmations. But just because something hasn't been proven yet, doesn't mean it isn't real. Take black holes. In 1916, Carl Schwarzschild realized that the equations of general relativity allowed for regions of space so dense that not even light could escape. And decades earlier, in 1783, John Michell, using only Newtonian physics, had proposed something similar. This means that for over 150 years, humanity only knew about the theoretical possibility of black holes, but had never seen one. It wasn't until 1971 that the first one, Cygnus X1, was identified for certain. It took almost 2 centuries to turn a hypothesis into reality. If it happened once, why couldn't it happen again? In the vast ocean of scientific ideas, there are possibilities so extreme and mysterious that they still escape our perception. Maybe the cosmos hides exotic stars, strange forms of matter, or even new states of space-time itself, phenomena predicted in equations but invisible to our eyes. What are these entities? No one knows for sure. For now, they are just theories, but I have some good bets. I'm Alex McColgan, and you're watching Galactic Legends. Today, we're exploring the strangest and possibly real objects in the universe, celestial bodies that might exist, if only we could find one. And who knows, maybe 188 years from now, someone will watch this video and see how many of them became reality. Perhaps this episode won't age very well, which deep down is something every astronomer hopes for. One of the first places to start this journey is, of course, with the stars. These plasma giants are some of the most beautiful and powerful creations in the cosmos. Through violent thermonuclear reactions, they release unimaginable amounts of energy, illuminating space and warming worlds around them. They are also the cosmic forges where the heavy elements that make up everything we know, including ourselves, are born. Astronomers have a good understanding of how stars live, shine, and die. We can even predict the fate of our own sun. In about 5 billion years, it will expand into a red giant. But today, we're not just talking about the stars we know. We're looking beyond the types of stars that might exist but have never been seen. Theoretical stars so strange that some might be made of a vacuum. But before we get there, we need to understand the basics. How a star stays alive. The closest example is our sun. It's not solid, it's a sphere of gas and plasma. If we tried to land on it, we'd be immediately pulled toward its center by gravity. So why doesn't the sun's own gas collapse? The answer lies in a constant battle between 2 extremes: gravity pulling everything inward and radiation pressure pushing everything outward. This pressure comes from the energy generated in the core, from the nuclear fusion that turns hydrogen into helium. Each photon released pushes the solar plasma a little, balancing the force of gravity. This delicate equilibrium between collapse and expansion is what defines a star. When the sun runs out of hydrogen, it will start fusing helium into heavier elements, carbon, oxygen, and so on. But one day, even those fuels will run out, and what's left will collapse, forming a white dwarf. In these dead stars, there's no more fusion. So, what prevents total collapse? A new form of resistance emerges: electron degeneracy pressure, a quantum effect that prevents electrons from getting too close to each other. But if the star's mass is too great, even that isn't enough. This limit is known as the Chandrasekhar limit, about 1.4 times the mass of the sun. Above that, the white dwarf collapses even further, forming a neutron star where matter is compressed to almost unimaginable densities. And yes, there's a limit for that too. If the mass exceeds about 2.2 times that of the sun, not even the quantum pressure of neutrons can hold it up. Gravity wins, and the collapse is endless. A black hole is born. That's a lot of pressure for one star. But then, what really happens inside a black hole? What lies beyond the point of no return, the event horizon? Einstein's equations of general relativity accurately describe how space and time curve around a mass. And inside a black hole, this curvature becomes infinite. At the heart of this mathematical abyss is the singularity, a point where our laws of physics simply stop working. For scientists, this is like a red flag, a warning that something is missing from our theory. And, of course, where there's a limit, there's curiosity. Does nature really allow for infinite singularities? Or does the universe have a trick up its sleeve, something that prevents total collapse before that point? This is where the boldest hypotheses begin. Scientists started to imagine an alternative. What if, instead of a singularity, what we call a black hole was something different, ... Something with an exotic and stable interior. This led to the idea of gravastars, short for gravitational vacuum stars. Imagine a star so compressed that the matter at its core doesn't collapse infinitely, but transforms into something entirely new. A kind of negative energy vacuum that repels gravity instead of attracting it. This internal vacuum would act like an elastic barrier, preventing total collapse and balancing the gravity of the outer layer, a thin shell of ultra-dense matter. From the outside, a gravastar would look just like a black hole in every way. It would have mass, spin, and a boundary from which nothing can escape. But internally, it would be radically different. No singularity. No infinite destruction of spacetime. Just a strange balance between gravity and anti-gravity, a cosmic echo of a collapse that almost was but never came to be. The most curious part? This idea could solve some of the deepest paradoxes in modern physics, like the black hole information paradox. If gravastars really exist, they could store and release information in a way that black holes can't, reconciling general relativity and quantum mechanics. But for now, it's still a hypothesis. There's no definitive observation capable of distinguishing a regular black hole from a gravastar. And if there's one lesson the cosmos has taught us, it's that what seems impossible today might just be the first draft of tomorrow's reality. If black holes are regions of space where nothing can escape, then, by sheer symmetry, shouldn't there be an opposite? A place where nothing can enter? This is the idea behind white holes. While a black hole swallows everything around it, matter, radiation, and even time itself, a white hole would do the reverse. It would expel everything, rejecting any attempt to cross its boundary. In other words, a white hole is the mathematical mirror of a black hole, where the flow of time is inverted. When physicists looked closer at Einstein's equations, they noticed something surprising. The same formulas that describe black holes also allow for solutions that behave exactly like white holes. And most intriguingly, in certain models, a black hole and a white hole can be connected like two sides of the same phenomenon. Imagine this: matter falling into a black hole at one point in the universe could, theoretically, emerge somewhere else, coming out of a white hole. This idea led to the notion of wormholes, cosmic shortcuts connecting distant regions of space and time. To visualize all this, physicists created an elegant way to represent spacetime: Penrose diagrams. In them, infinity is compressed into a two-dimensional map, where we can see how time and space warp near black holes, white holes, and other extreme structures. These diagrams showed that mathematically, the universe could contain regions interconnected by gravitational bottlenecks, bridges between collapse and expansion, between the birth and death of stars. It's an almost poetic vision, the universe recycling matter and energy, linking destruction and creation in an eternal cosmic cycle. Of course, so far, this is all purely theoretical. We've never observed a white hole, and the laws of thermodynamics suggest it probably couldn't exist in a stable form. Still, these concepts aren't a waste of time. They serve as thought experiments where we test the limits of the laws of physics. And every now and then, it's precisely at these limits that we find new windows to the truth. After white dwarfs and neutron stars, it seems there are no more rungs on the ladder of stellar density. But what if there was something even more compact? A final stage beyond the neutron star, a form of matter that only exists when the atom itself is destroyed. This is the idea of strange stars, also known as quark stars. A neutron star is essentially an atomic nucleus the size of a city. It's made almost entirely of neutrons, particles that, under normal conditions, are trapped inside atoms. But under pressures so absurd, they crush protons and electrons until they merge. The result is a homogeneous mass of neutrons compressed into a subatomic ocean. But there's a limit to even that. If the density increases further, the neutrons themselves start to break down into their fundamental components, quarks. Quarks are the most basic known particles of matter. There are 6 types or flavors: up, down, charm, strange, top, and bottom. Normally, they're confined in trios forming protons and neutrons. But in the extreme conditions inside a collapsing star, this boundary dissolves. The quarks are set free. A new state of matter emerges, a dense fluid of free quarks, so-called quark matter. If a star were made entirely of this material, it would be something completely new, a quark star, or more specifically, a strange star, if it contains strange-type quarks. The name might sound odd, but the behavior of this matter would indeed be strange in every sense. Unlike ordinary matter, it could be self-stable, meaning it wouldn't need gravity to hold itself together. This implies that small fragments of strange matter, called strangelets, could exist in isolation, floating through space like tiny nuclei, the size of mountains but with the mass of an entire asteroid. No one knows for sure if these stars exist, but some recent observations have raised intriguing suspicions. Certain pulsars rapidly spinning neutron stars seem too small for the mass they should have. Some astrophysicists believe they might actually be strange stars in disguise. If true, this would change our understanding of what's possible within matter. It would mean that in the depths of the universe, there are stars made of liberated particles, a direct glimpse into the first microsecond of the cosmos's existence. What if there were stars made of something completely different from ordinary matter? No electrons, no protons, no neutrons, something that emits no light but still exerts gravity. It sounds like something only fiction would invent. But curiously, this idea came directly from the equations of quantum physics. Every particle in the universe belongs to one of 2 families. Fermions, like electrons and quarks, which obey the Pauli exclusion principle, and bosons, like photons and the Higgs boson, which don't have this limitation. This means that while fermions resist being in the same place, bosons can occupy the same quantum state, behaving like a single coherent wave. And when many bosons come together like this, they form something called a Bose-Einstein condensate, a state of matter where all the atoms act in perfect unison. Now imagine a condensate on a cosmic scale, a gigantic sphere made of boson fields held together only by gravity and quantum laws. This is the idea of boson stars. They will be completely invisible, no light, no heat, no radiation, but with enough mass to bend space-time around them. From the outside, they would resemble black holes. But unlike them, they would have no event horizon, which means information wouldn't be lost inside them. And here comes the most fascinating detail. If dark matter is composed of boson-like particles, as some models suggest, then boson stars could actually exist formed by the condensation of this invisible matter. In other words, there might be real dark matter stars scattered throughout the cosmos, silent, transparent, and untouchable, but with the same gravity as an ordinary star. Perhaps we've already passed through one without even noticing. These objects would challenge our observational tools. They wouldn't emit light or block radiation. They would only be detectable by the gravitational effects they cause, bending the paths of nearby stars or distorting the light from distant galaxies. But, if confirmed, boson stars could offer us the first concrete clue about the true nature of dark matter, one of the biggest mysteries in modern physics. And who knows, reveal that the universe is inhabited not only by stars of fire and plasma, but also by stars of shadow and silence. Let's go back in time. More than 13 billion years ago, right after the Big Bang, the universe was a hot, dark ocean, filled with primordial gas and invisible matter. The first stars had not yet been born. Space was silent, marked only by gravity, which slowly began to pull hydrogen and helium into ever denser clouds. Over time, these clouds collapsed under their own weight, igniting the first cosmic fires. These would be the population 3 stars, the very first stars in the universe. But some scientists believe that not all of them ignited the way we imagine. What if, instead of being powered by nuclear fusion, these first stars had another energy source? Something invisible but incredibly powerful. This is the idea of dark stars. According to some models, in the early universe, the density of dark matter was much higher than it is today. And if this matter is made of particles that annihilate each other on contact, they could release enormous amounts of energy enough to inflate and heat a young star. These stars would be gigantic, thousands of times larger than the Sun, but much cooler and more diffuse. They would shine not from fusion, but from the constant annihilation of dark matter in their core. They would be, in essence, stars made of shadow.